All right, so the first thing I'm going to talk about is the notion of like positive definiteness and positive semi-definiteness and related notions. And then after that, I'll talk about the Cholesky factorization, which is a factorization that's specific for positive definite matrices. You can also do it for positive semi-definite matrices as well. All right. So first, I just want to kind of quickly recall what we've talked about in the last review that I did. So last time I talked about diagonalization. So just a recap of how that works is if you have an n by n matrix A, if you are able to find n linearly independent eigenvectors, and then let's say that lambda 1 through lambda n are the corresponding eigenvalues, then we can factor the matrix A as PDP inverse, where matrix P has the eigenvectors as its columns, and then the matrix D is a diagonal matrix with the corresponding eigenvalues along its diagonal, okay? And then for symmetric matrices, they were a little bit special. So for a symmetric matrix, you are, if it's a n by n symmetric matrix, you are always able to find n orthonormal eigenvectors. So if you use these orthonormal eigenvectors, you can diagonalize your matrix as usual. But since the columns of Q are orthonormal, it turns out to be an orthogonal matrix, so that its inverse is actually the same as its transpose. So then this factorization of a symmetric matrix using the orthonormal eigenvectors, this is called the spectral decomposition. And it's something that you can only do for a symmetric matrix. Okay, so now I'll start talking about the new material. So first I'm going to define a couple of notions. So all these are going to be specific for symmetric matrices. So we'll assume A is symmetric. Okay. So we say that matrix A is positive definite if all of its eigenvalues are positive. Okay. And there are some related notions. So we also say that A is positive semi-definite if all of its eigenvalues are non-negative. Okay. So the difference between positive definite and positive semi-definite is if it's positive definite, all of its eigenvalues are strictly positive, so all strictly greater than 0. If it's positive semi-definite, then they're all non-negative, meaning greater than or possibly equal to 0, okay? And this is probably not as important, but I'll mention these anyway. So you can also say that a symmetric matrix is negative definite and negative semi-definite. Depending on whether its eigenvalues are all negative or if they are all, I guess, non-positive. Okay. Meaning for negative definite, they all have to be strictly less than 0. If it's negative semi-definite, they are less than or possibly equal to 0. Okay. All right. So here I've defined these 4 notions in terms of the eigenvalues of the symmetric matrix. There is another definition that is not directly in terms of its eigenvalues, so I'll also state that equivalent definition. Okay. So then equivalently, we can say that A is positive definite if X transpose times A times X is positive, or so greater than 0, for every X that's not equal to 0. And then an equivalent definition to be positive semi-definite is for X transpose AX to be greater than or equal to 0 for every, I guess you can say for every X. When X is 0, it's definitely going to be 0. Let's see here. And then equivalently, A is negative definite if X transpose AX is strictly less than 0 for all non-zero X. And then equivalently, A is negative semi-definite if X transpose AX is less than or equal to 0 for every X, okay? Okay, so then here, these are equivalent definitions. So what that means is if you have a symmetric matrix, all of whose eigenvalues are positive, then it will also be true that X transpose AX will be greater than 0 for every non-zero X. So in that sense, you can use either of these 2 definitions to define what it means to be positive definite, and then et cetera for the other ones as well, okay? All right, so for those of you who are just joining, if you have any questions at any time, you can either post a question in the chat, or also I have enabled audio for this review. So you can also turn on your mic to talk to me directly if you had a question, okay? And you can just interrupt at any time if you have a question. All right. Okay, so right now, if you have a symmetric matrix, and let's say you want to check it is positive definite, so one way to do that would be to just calculate all of its eigenvalues and check if all of them are positive. Another way to do that, which is maybe a little bit more difficult, is to check if X transpose AX is going to be positive for all non-zero vectors X. But there's another way to check if a symmetric matrix is positive definite, which is maybe a little bit easier. So that will be the subject of this theorem that I'm about to state. So again, let's assume that A is a symmetric matrix. Okay. And so I'm going to, for this theorem, I'm going to define AK to be the upper left K by K submatrix of A, okay? So as an example of that, let's say if I create a 3 by 3 matrix to illustrate. Okay. All right, so then like A1 would be the upper left 1 by 1 matrix. So it would just be the upper left corner entry. And then A2 is the upper left 2 by 2 submatrix. So it would be, here it would be this 2 by 2 A, B, B, D. And then A3, the upper left 3 by 3 submatrix would just be the entire matrix A, okay? All right. So then this theorem says that a matrix A is positive definite if and only if the determinant of all of these submatrices is positive. Okay? So I will do a quick example of that. Let's say I have this symmetric matrix A. It's going to be 3, 1, 0, 1, 2, 1, and 0, 1, 3. So for this matrix A, I want to check, is it positive definite or not? Okay, so to check if A is positive definite, I'm going to, using this theorem, what I'm going to do is I'm going to look at the 3 upper left submatrices that we get. So A1 would just be 3. A2 would be 3, 1, 1, 2. And then A3 would just be the entire matrix itself. Okay, so what I'm going to do right now is I'm just going to compute the determinant of each of these matrices. So starting with determinant of A1. So determinant of a 1 by 1 matrix would just be itself. So determinant A1 is 3. Now if we check the determinant of A2, so that's going to be 6 minus 1. So that'll be equal to 5. And then looking at the determinant of A3. All right, so for this 3 by 3 matrix, let's get the determinant by doing cofactor expansion. So I'll do expansion along the first row. So I'm going to take the 3 and then cross out the first row in the first column. And then I need the determinant of this remaining 2 by 2 matrix. And then next we're going to do minus 1 times, and then I'm going to cross out the first row in the second column. We have 1, 1, 0, 3 remaining. And then the last one is plus 0. And let's go ahead and compute what all of this will be. So we've got 3 times 6 minus 1, so 3 times 5. Here we have minus times 3. So that leaves us with determinant being equal to 12. Yeah. And so since the determinants of each of these submatrices, since they were all positive, then this theorem allows us to conclude that the matrix A is, in fact, positive definite. Okay. All right, so that's just a quick illustration of using this theorem to check if a matrix is positive definite. Okay, so since this matrix A is positive definite, if you were to try to calculate its eigenvalues, you would find that all of its eigenvalues are going to be positive. So that would just confirm that it was in fact a positive definite matrix. Now I want to talk a little bit more about this theorem right now. So just going back to the theorem. Okay, so what the theorem says is for a symmetric matrix A, if the determinant of all of these like upper left submatrices, if all of them are positive, that is equivalent to the matrix A being positive definite. Okay. Okay, so then we might wonder, what if all of the determinants were not positive, but what if they were all greater than or equal to 0? Okay. So if all of them were greater than or equal to 0, could we say that the matrix A is positive semi-definite? So it turns out that the answer is actually no. Okay. So just an example of a matrix where all of these upper left determinants are greater than or equal to 0. Okay. But nevertheless, the matrix is not positive semi-definite. So here I have an example where if you check each of the upper left submatrices, all of them have determinant equal to 0. But when you look at this matrix, this is already a diagonal matrix. So its eigenvalues are simply going to be its diagonal entries. So in other words, the eigenvalues of this matrix are 0, 0, and -1. So in fact, this matrix is not positive semi-definite. It's actually, in fact, negative semi-definite instead. Okay.
Yeah, so if that theorem said if determinant of A of k is greater than 0 but not equal to, is that fair or no?
Yeah, so if all of them are positive, then the matrix will be positive definite. But if all of them are greater than or equal to 0, you cannot say that's positive semi-definite. Okay?
Okay.
All right. Now there is a related theorem for like negative definite matrices. I don't think that's too important though. So I think, well, I guess I'll go ahead and state it. It doesn't take long. Let me make a quick comment about what I just said though. So what I said does, it does work for the special case where your matrix is 2 by 2. So it is true that if A is 2 by 2, then if all of these upper left determinants are greater than or equal to 0, actually, wait, I guess it wouldn't work because this would be, oh, that's interesting. Okay, never mind. That's actually not true, so I'll get rid of that. Okay, that's interesting. Okay, so just forget what I was about to say, but let me just state the related theorem for a negative definite matrix real quick. So A is going to be negative definite if and only if the determinants of all the upper left submatrices. Okay, so here it's it's actually not the case that if all these determinants are negative, then it's going to be negative definite. So instead, to be negative definite, these determinants, they have to alternate in sign. So the first one has to be negative. The second one has to be positive, and then it has to keep alternating as such, okay? And then one way you can sort of phrase it is to say that the sign of these determinants must be equal to -1 to the k. Okay. So when k is odd, it has to be negative. And when k is even, it has to be positive, okay? But okay, I don't think that's as important. So I feel like positive definite matrices are more important than negative definite matrices. They come up often in some applications, so that's why I guess they are important. Okay. All right, now let's see here. So I'm going to talk about the Cholesky factorization, but before I do that, I'll just state one fact which will tie into the singular value decomposition when I talk about that later. Okay, so let's say I have some matrix A. Okay. It doesn't even have to be square, so it could be just any size m by n. And so for any matrix A, the matrices A transpose A and A transpose. So these matrices are always positive semi-definite, okay? So they may be positive definite, but at the very least, they're always going to be positive definite. And here it's this is simple enough to prove, so I think I'll go ahead and prove it. All right, so to show that these matrices are positive semi-definite, I want to show that the eigenvalues are always greater than or equal to 0. So I'll do it for A transpose A, and the proof for A transpose will basically be the same pretty much, okay? First, let's go ahead and note that A transpose A is in fact going to be a symmetric matrix. Okay, so why is it a symmetric matrix? So remember that to be symmetric, a matrix, for a matrix to be symmetric, it has to be equal to its own transpose. So if we transpose A transpose A right now, so if you remember how the transpose of a product works, I'll write it over here. So when you transpose something like AB, you transpose each matrix individually, but you also write it in reverse order. So it goes B transpose and then A transpose. So if I apply that rule to A transpose A, that means we'll have A transpose first. And then we'll have A transpose transposed second. And of course, A transpose transposed is just the original A. So this shows that the transpose of A transpose A is itself. And that would prove that it is a symmetric matrix, okay? So then next, to show that's positive semi-definite, I want to show that all the eigenvalues are greater than or equal to 0. So to show that, let's suppose that x is an eigenvector of A transpose A, and that lambda is the corresponding eigenvalue. So what I'm going to do with this equation is I'm going to multiply both sides of this equation by x transpose on the left. Okay. All right, and then something that you guys might be familiar with, but maybe just in case you're not. So whenever you have a vector transpose times another vector, that's going to be the same as the dot product of those two vectors. So I know I've talked about it before in my reviews, but for someone who maybe didn't attend my reviews, who is here, and if you're maybe not too familiar with this result, here just illustrating with vectors in R2. So if I take a vector u and transpose it, meaning I write it as a row, and then I times a vector v, which is just written as a column. If you do the matrix multiplication, you get like u1 v1 plus u2 v2. And that is precisely the dot product of these two vectors u and v, okay? All right, so in other words, what I have here is x dot product with itself. And when you have a vector dot product with itself, that gives you its length or its norm or its magnitude squared. Now on this side, okay, so notice on this side, we can rewrite it as AX transpose times itself. Because here, transposing AX would give you X transpose first and A transpose second. So in other words, you've got AX dot product with itself. So on the left, you have the length of AX squared. So then, of course, when you have the length of a vector squared, that has to be greater than or equal to 0. So in order for the right-hand side to be greater than or equal to 0 to match the left-hand side, that means that your eigenvalue has to be greater than or equal to 0 as well, okay? So that's kind of a proof that the eigenvalues must be greater than or equal to 0. So therefore, that proves that A transpose A is a positive semi-definite, all right? Okay, so any questions about that? Okay. So the proof is not super important, but because it was fairly short, I decided I would go ahead and write it out. And so this fact that A transpose A and A transpose, the fact that they are positive semi-definite, that does come into play a little bit when I talk about the singular value decomposition later. So right now, I'm just going to talk about the Cholesky factorization real quick. Okay. So this is a factorization that's specific for positive definite and positive semi-definite matrices. And I'm going to go ahead and illustrate first with an example. And then after the example, I'll go ahead and summarize the procedure for calculating a Cholesky factorization. Oh, maybe I should say what it is first. Okay, so before that. So the Cholesky factorization is factoring a positive definite or positive semi-definite matrix as a C transpose times C, where matrix C is an upper triangular matrix. Okay. All right, and so in order to calculate the Cholesky factorization, so I'm going to take this A that we used earlier. Okay. So earlier we verified that this matrix is positive definite by checking the determinants of all the upper left submatrices, and we saw that all of them were positive, okay? So now that we know this matrix is positive definite, we can try to find a Cholesky factorization for it. So the procedure for calculating a Cholesky factorization is you want to start by getting an Ldu factorization of the matrix first, okay? So LDU is something that we did like way back, I think it was before the first exam actually, so very early on in the semester. So the way that works is you want to start by reducing the matrix to an upper triangular matrix. Now I want to reduce the upper triangular without swapping any rows, and I don't want to like multiply a row by a constant either. All I want to do is add or subtract a multiple row to another row. Okay. So I have to use this 3 as a pivot to do the elimination first. So to eliminate the 1 beneath it, what I'm going to do is I'm going to do row 2 minus 1/3 of row 1. Okay. All right. So let's see here. I'm going to get 2 minus 1/3, which would leave me with 5/3. And then 1 minus 0, so that'll be 1. Okay. So next I have to use 5/3 as my pivot to eliminate the 1 beneath it. So let's do row 3 minus 3/5 of row 2. Okay. Okay, so let's see, for the final entry, we'll have 3 minus 3/5. So 3 is 15/5 minus 3/5, so that'll be 12/5, okay? All right, so now we've reduced A to an upper triangular matrix. Now, I'll call this U for the moment, although we're going to get another U later on. Okay, so if you guys remember, to get the lower triangular matrix L, we had 1s on the diagonal, and then because it's lower triangular, we have 0s above the diagonal. And then we get the entries beneath the diagonal based off the row operations that we performed. And the way that I always thought of it was whatever like number you're using in your row operation, you change the sign, and then you place it in the corresponding entry of L. So for instance, the 2, 1 entry of L, here I did row 2 minus 1/3 of row 1. So I'm going to take that negative 1/3, I'm going to change the sign to make it positive 1/3, and then I place it in the 2, 1 position. Likewise over here, from this row operation, I'm going to put a positive 3/5 in the 3, 2 position. And since I never did a row 3 plus or minus something row 1 operation, then I'll just put a 0 in this entry. Okay, so then with that gave us an Ldu factorization of A. But what we want right now is an Ldu factorization. So then if you remember how Ldu works, so the way that worked is we're going to take this upper triangular matrix that we found earlier. We're going to take the diagonal entries and put them into a diagonal matrix. So that gives us a diagonal matrix D. And then we're going to get a new matrix U. And then this U is obtained by dividing each row of the original U by the pivot, okay? So I divide the first row by 3 to make it 1 1/3, 0. I'll divide the second row by 5/3, or if you will, I'll multiply the second row by 3/5. So that'll be 0, 1, and 3/5. And then divide the last row by 12/5, or if you will, multiply by 5/12. So then with the L as before, D and then this new U, that gives us the Ldu factorization of our matrix, okay? And because our matrix A was a symmetric matrix, notice that the matrices L and U happen to be transposes of each other. So L is U transpose, or maybe I'll write it as L transpose is U. So since U is L transpose, our LDU decomposition actually becomes like an LDL transpose decomposition. So I don't know if you guys remember way back early in the semester how you had problems where you were given a symmetric matrix and you were asked to find the LD L transpose decomposition. And that amounted to just finding an LDU decomposition, and then the U turns out to be the transpose of the L, okay? Okay. Now what we wanted though was a Cholesky factorization, which is supposed to look something like this, C transpose C, where C is upper triangular. Okay. So in order to get the Cholesky factorization, what we are going to do at this point is I'm going to take the diagonal matrix D that we got earlier for the LDU or LDL transpose decomposition. And because our matrix was positive definite, the diagonal entries of this matrix D are all positive. Okay. And so if your matrix was positive semi-definite, it would turn out that all the diagonal entries of D are greater than or equal to 0. Okay. So because of that, what we can do is we can square root this diagonal matrix just by square rooting each of the diagonal entries. Okay. So then what we're going to do is in the LD L transpose decomposition, we are going to split the matrix D into two matrices by taking its square root. Okay. All right, so then when we do this, when we split our diagonal matrix into two by using its square root, what will happen is these matrices that we get here are going to form the matrices for our Cholesky factorization, okay? All right, so let's see here. I'm going to compute this part here, this term on the right, in order to get the matrix C. So here's the square root of D, and L transpose earlier was this upper triangular matrix. So I want to multiply these two matrices together in order to get the matrix C that we need for the Cholesky factorization. So if we just do the multiplication real quick, we're going to square root of 3, 0, 0, 0. And then let's see here. This will be, see here, that times this will be 0. So square root of 5/3. Let's see here. This times, oh wait, no, not that entry. That one is 0. This one is square root of 5/3, I believe. Yeah, okay, and then this one times this one is, so we've got square root of 5/3 times 3/5. Let's see here. Okay, I need to do this more slowly, so give me a second. Okay, let's do it one at a time. So row times column is √3. I know it should be upper triangular, so I'll fill in zeros for these. Okay, so I'm going to do row times second column. Okay, so √3/3. And then row times the third column. Looks like that one is 0. Then row times this column to get this entry. So that will be square root of 5/3. And then row times column. So it looks like that would be 3/5 times square root of 5/3. Which I suppose we could simplify, but maybe I'll save that for the end. The last entry will be this row times this column, which will give me square root of 12/5. All right, and then let me see here, we can simplify this as √3/5. All right, so then that means matrix C is going to be √3, √3/3, 0, 0, √5/3, √3/5, 0, 0, and then √12/5. All right. So then with this matrix C that we have, we'd be able to factor the matrix A as C transpose C. And then that would have been the Cholesky factorization of the matrix A, all right? Okay. So then the general procedure for calculating the Cholesky factorization. So remember, first it only applies if your matrix is positive definite or positive semi-definite. If that's the case, just find the LDU decomposition. That will turn out to be an LDL transpose decomposition, although I think that's not super important for us. And then the matrix D will have positive or at least non-negative entries on the diagonal, so that you'll be able to square root it by square rooting each of the diagonal entries. And then by splitting your diagonal matrix into 2 with its square roots, you can then calculate the matrix C as being the square root of D, and then times the U that you had in the LDU decomposition. Okay. All right, so then I'll just maybe pause for a moment. So if anyone has a question, you can ask. Okay, so in that case, I'll move on to the singular value decomposition, which is where I'll spend the rest of the review talking about. So Cholesky's factorization, it's useful in simplifying and or speeding up certain algorithms that involve positive definite or positive semi-definite matrices. So that's like one kind of application of it. All right, but now I'm going to move on to the singular value decomposition. So let's talk about what that is first. So the singular value decomposition, it's actually kind of similar to like the spectral decomposition, but whereas the spectral decomposition was only for symmetric matrices, the singular value decomposition, it actually works for any matrix, including like non-square, so rectangular matrices. So every matrix can be factored into a singular value decomposition, okay? Now there's kind of two versions of the singular value decomposition. The reduced and then the full singular value decomposition. So as the names kind of suggest, the reduced singular value decomposition is a little bit like smaller than the full one. So it's a little bit easier and a little bit quicker to compute, okay? So I'm going to start by talking about the reduced singular value decomposition. And then after that, I'll talk about the full singular value decomposition. Okay. So here I've already written out some of the information for the reduced SVD. So if I have a matrix A, which is just a generic size m by n, the singular value decomposition will factor the matrix A into a product of three matrices. Okay. So I've labeled these matrices as U, sigma, and then V transpose. And I've placed a plus sign as a subscript on each of these three matrices, okay? Now the plus sign as a subscript is my own like personal notation right now. So I don't know if like your professor uses a different notation, or if your textbook uses a different notation. This is the notation that I'm using. I'll explain why I put a plus subscript on it, okay? Now I've indicated the size of the matrices. So this U with a plus subscript will be size m by r. This sigma in the middle will be a square matrix size r by r. And then this V transpose matrix will be size r by n, meaning that V itself would have been size n by r, okay? Now this r that's appearing right now, that does happen to be equal to the rank of the matrix A, okay? So that's what the r actually represents. And then here I have a couple of comments about each of these three matrices. So starting with the sigma plus in the middle. So this matrix in the middle is going to be a diagonal matrix. The entries on its diagonal are going to be the square roots of the positive eigenvalues of A transpose A and A transpose. So we talked about how like A transpose A and AA transpose are both always going to be positive semi-definite. So all of their eigenvalues are going to be greater than or equal to 0. So for the reduced singular value decomposition, we only need to look at the positive eigenvalues, and we can ignore the any 0 eigenvalues that they may have had. And so because we're only looking at the positive eigenvalues, that's why I placed a plus sign as a subscript on each of them, just to sort of emphasize that's really looking only at the positive eigenvalues. Okay? Now, I'll also note something that I'm kind of stating right now in the statement is that A transpose A and AA transpose, they will actually have the same positive eigenvalues. Okay. So if you take the positive eigenvalues that they have and you square root them, those would be what you place in the diagonal matrix sigma plus here. Okay. And the square roots of the positive eigenvalues, those are called the singular values of A. Okay, so just some terminology there. In applications, we typically order the singular values from largest to smallest. So there's a sense that the largest singular values are the most important ones, and the smallest ones are the least important. So ordering them from largest to smallest is kind of a reflection of that fact, all right? Now, going on to the matrices U and V. Okay. So the columns of V plus are orthonormal eigenvectors of A transpose A, corresponding to its positive eigenvalues. And the columns of U plus are orthonormal eigenvectors, but for A transpose instead of A transpose A, okay? And again, it's corresponding to the positive eigenvalues only. So the fact that A transpose A and AA transpose are symmetric is what will guarantee that you will be able to find these normal eigenvectors, okay? All right. So then I'm going to talk about the procedure for finding the reduced singular value decomposition of a matrix. And then after that, we'll do some examples, and then I'll talk about the full SVD at the end, or towards the end. Okay. So let's say I have a matrix A, which is size m by n, and I want to find a reduced SVD for it. Now here, I've kind of split it into two methods, if you will, for finding the reduced SVD. So method one is finding the sigma and then the V, and then finding the U at the end. And then method two is just flipping that slightly and finding sigma and U first, and then finding V at the end instead, all right? So you can use either of these two methods to calculate the SVD, it doesn't matter which one. So let's take a look at method one first. So what you'll do is you'll start by finding the positive eigenvalues of A transpose A, and then finding corresponding orthonormal eigenvectors, okay? So let's say you calculate the eigenvalues of A transpose A, and here I've ordered them from largest to smallest. Okay, so lambda 1 is the largest one, lambda 2 is the next largest one, and so forth. So then lambda r will be the smallest one, which was positive. And then the rest of the eigenvalues, if there are any, would be equal to 0, okay? And then V1, V2, and VR, these would have been the orthonormal eigenvectors that you found, corresponding to these positive eigenvalues. So then what you'll do is you'll square root each of the positive eigenvalues to get the singular values. And then place the singular values along the diagonal to get the sigma plus matrix. And then take the orthonormal eigenvectors that you found and just put them into a matrix as columns to get the matrix V plus. Now finally, to get the matrix U plus, what you'll want to do is use these formulas. So U1 is 1 over sigma 1, AV1, U2 would be 1 over sigma 2, AV2, and so forth. So doing that, you'll calculate these vectors, U1 through UR, and then just put those into a matrix as columns, and that will give you the matrix U plus. Okay. So then with the sigma V and U plus, you'll get the reduced SVD of A, all right? So that's method one. Method two is basically the same, except you'll start with A transpose instead of A transpose A. So you get the eigenvalues, and you only need to focus on the positive ones. You get the corresponding orthonormal eigenvectors. Now this time, if you start with A transpose, then the eigenvectors that you're calculating will form the matrix U instead of the matrix V, okay? So square root the positive eigenvalues to get the singular values, and again, that will form the matrix sigma plus. And then again, the corresponding orthonormal eigenvectors here will give you the matrix U instead of V. And then you'll use these formulas down here. So V1 is 1 over sigma 1 A transpose times U1, and so forth. You'll calculate these vectors V1 through VR, and then put those into a matrix as columns, and that will give you V plus, okay? So either of these two methods can be used for calculating the SVD or the reduced SVD of a matrix. So it's up to you. You can just memorize one of them and then just use that every time. But here I wanted to just make a little observation that if your matrix is size m by n, so in method one, when you're looking at A transpose A transpose A will be size n by n. Whereas in method two, when you're looking at A transpose, it's going to be size m by m instead, okay? So it might be easier to start with whichever one was the smaller matrix, because if your matrix is smaller, in theory, it'll be a little bit easier to find its eigenvalues and eigenvectors, okay? So that's kind of one way that you can determine for yourself if you want to use method one or method two, is to observe whether A transpose A or A transpose is smaller, and whichever one is smaller would determine which method you want to go with, all right? That being said, though, all of your matrices are going to be small enough as to where, like, it's going to be probably 2 by 2 or 3 by 3. And I guess in both of those cases, they're small enough as to where it wouldn't really matter. So you can just stick with one method all the time, and that would also be perfectly fine, okay? All right, so I'm going to do some examples right now. I'll do 2 examples of calculating a reduced SVD. So let's see here. I'm going to start with a 3x2 matrix A. So I'm going to do A is 3, 1, 1, and then 1, negative 3, and 2. Okay, so here, since n is smaller than m, then I might prefer to go with method 1 and calculate A transpose A, since that will be smaller than A transpose, okay? So I'm going to use method 1 to calculate the reduced SVD right now. So that means what I'm going to do is I'm going to start by calculating A transpose A. Okay, so I'm going to transpose A, then times A. Let's see what the result will be. So we'll get 9, 10, 11. Next will be 3 minus 3 plus 2. And then last will be 1 plus 9 plus 4. So I think that's 14. Okay. Okay, so now that I have A transpose A, what I want to do is I want to find its eigenvalues and its eigenvectors. So for the eigenvalues first, I'm going to do the determinant of lambda I minus A transpose A. So that's going to give me lambda minus 11 and lambda minus 14 on the diagonal. And then since I'm subtracting the H transpose A, I'm going to have minus 2 and minus 2. Many of you would prefer to do H transpose A minus lambda I, and that is perfectly fine. Okay. But I'll leave it the way that I've written it. And then we're going to get the determinant to get the eigenvalues. So first, we'll get lambda minus 11 times lambda minus 14. I'm going to go ahead and distribute all of that out. So I'm going to get lambda squared minus 14 lambda minus 11 lambda for a total of minus 25 lambda. And then 11 times 14, I think that's going to be 154. And then we have that, and then minus positive 4. Okay. So it'd be minus 25 lambda plus 150. And then let's see here, if I want to factor that, see here, I think minus 30 and plus 5. No, that doesn't work, does it? Because that would be minus 150. Oh, but this was it minus? No, it was plus. Okay, so that doesn't work. Let me see here. Okay, 15, minus 15, and minus 10. Okay. Okay, yeah, so that would add up to negative 25 and multiply to be positive 150. Great. Okay. So then we have 2 eigenvalues. Lambda 1 would be the largest one, 15. And then lambda 2 will be the next largest one, which is 10. So in this case, we didn't have any 0 eigenvalues. But if we did, then you could just ignore them for the reduced SVD, okay? All right. So now that I have the eigenvalues, first we can go ahead and get the singular values by square rooting these eigenvalues, okay? And then I can go ahead and write out what the matrix sigma plus would be. So it's a diagonal matrix with the singular values along its diagonal, okay? So that's good. All right, so next I need to get the eigenvectors corresponding to these eigenvalues. So let's start with the largest eigenvalue first. Okay. So to get the eigenvalues, I need to look at the matrix 15I minus A transpose A. And so let's see, if I plug in 15 for lambda up here, we'll get 4 and 1, and then minus 2, minus 2. And then remember that to get the eigenvectors, you want to look at the null space of this matrix. So to get the null space, I can do some row operations. So let's say if I divide row 1 by 2, and then add row 1 to row 2. Okay. So then here we've reduced our matrix a little bit, and now looking at the null space, what I'll do is from the first row, I'll write out the corresponding equation, 2x minus 1y equals 0 for the null space to get the eigenvectors. Let's see here. I guess I'll go ahead and write it as y equals 2x. So if I choose x, the free variable this time, then we'd have y is 2t. And from that, if I factor the t out from everything, I'll get the vector 1, 2. So this would be 1 eigenvector corresponding to the eigenvalue of 15 that we found, okay? And so I'm going to go ahead and find another eigenvector for the other eigenvalue first. So next, lambda 2 was 10, so let's find an eigenvector for this guy. So looking at 10I minus A transpose A. So looking at the original lambda I minus A transpose A matrix, I'm going to plug in 10 for lambda. So it'll be -1 and -4 on the diagonal. And then it was -2 off the diagonal. So let's say if we did some row operations real quick. Let's say multiply row 1 by -1. And then row 2 plus 2 of row 1. Okay. So then from that, we get the equation 1x plus 2y equals 0. Here, let's do x is -2y. So if I choose y to be the free variable, we could write x as being -2t. And then looking at just the coefficients of t, we will get -2, 1 as one of the eigenvectors, okay? Now for the SVD, we need orthonormal eigenvectors. So right now, the vectors that we found, they are orthogonal to each other already. So 1, 2, and -2, 1. So they're orthogonal because they were eigenvectors corresponding to distinct eigenvalues of a symmetric matrix. So to make them orthonormal, we do need to normalize each of them as well. Okay, so to normalize, we'll divide each of them by their length. So here the length of this vector would be square root of 1 squared plus 2 squared. So divide square root of 5. It's going to give us v1. And then this guy has the same length. So square root of -2 squared plus 1 squared is root 5. Okay. So then normalizing them gives us the vectors v1 and v2. And then with that, we could write out the matrix V plus as, so v1 was 1 over root 5, 2 over root 5, and then here it's -2 over root 5 and 1 over root 5. All right. Okay, so with that, we now have the matrix V plus. We also had the matrix sigma plus from earlier. So the last thing we need to do is we also need to calculate the matrix U plus. So we'll do that. Okay. So in order to get the matrix U plus, so we had these formulas from before. So U1, we'll calculate U1 as being 1 over sigma 1 times A V1. And then likewise, U2 is 1 over sigma 2 A V2, okay? All right, so let's see. We'll calculate U1 first. So it was 1 over sigma 1. The first singular value was the square root of 15. And then that's going to be times matrix A. So from the beginning, A was 3, 1, 1, 1 minus 3, 2. And then V1, which we just found earlier, it was this vector, 1 over root 5 and 2 over root 5. Yeah. So I'm going to go ahead and factor the square root of 5 out to the front. So 15 times 5 will give us square root of 75. And then just multiplying these out, we're going to get 1 over root 75. And then let's see, we'll get 3 plus 2 is 5. 1 minus 6 is -5. And then 1 plus 4 is 5. Oh, that's pretty nice. Okay. All right. And I guess it's not super important, but this, we can simplify this pretty nicely. So square root of 75, we can write it as square root of 3 times square root of 25. And square root of 25 is 5. So then we can cancel these 5s with this 5 in the denominator. which would leave us with this at the end for U1. And then we'll also need to calculate U2. So it was 1 over sigma 2, so 1 over root 10. And then times A, which was 3, 1, 1, 1, negative 3, 2. And then vector V2 was over here. Okay. So I'll go ahead and put the root 5 in the front again. So multiplying root 5 into the denominator here will give me root 50. And then we just had negative 2, 1 remaining. So let's go ahead and just multiply these out real quick as well. So that's going to be negative 6 plus 1 is negative 5. Negative 2 minus 3 is negative 5. And negative 2 plus 2 is 0. And it's maybe not that important, but if we simplify this, the square root of 50 is square root of 2 times square root of 25. And then killing the 5 would give us 1 over root 2, and then times negative 1, 0. Okay. So then now that we have vectors U1 and U2, I'll just put them into a matrix as columns to get the matrix U plus. Okay. All right, so then with this, and then with V plus from here earlier, and then the sigma plus that we had over here. With those three matrices, that will give you the reduced singular value decomposition of the matrix A, okay? So if you were to multiply it out, like U plus times sigma plus, and then times V plus transpose, that product should give you the original matrix A, all right? Okay, so then it's a pretty long procedure. Do you guys have any questions about that? Okay. All right, so let's see here. So then just to kind of illustrate, I'll try to do another example, hopefully a little bit more quickly. Well, okay, not yet. I guess before that, let me talk about the full singular value decomposition first. Okay. Okay, so for the reduced, as we talked about how that's when you factor your matrix A, into three matrices. We tried to note it as U plus, sigma plus, and then V plus transpose. And then I noted the sizes of each of these matrices, R being the rank of A. So the full SVD, what that does is it factors a matrix A into like a similar product of three matrices. But this time the matrices U and V are going to be square matrices, M by M and N by N. And then the matrix sigma in the middle is going to be M by N, the same size as the original A. Okay. And basically the difference between the full SVD and the reduced SVD is, and the reduced we did not bother finding eigenvectors corresponding to any zero eigenvalues that we may have had. But for the full SVD, we would also need to look at the zero eigenvalues of A transpose A and A transpose and find those eigenvectors, and those would be added into the U and the V to get these two matrices. And then the sigma in the middle is still kind of a diagonal matrix with the singular values on its diagonal, except you would add zeros to it afterwards to make it the same size as A. So let's talk about that a little bit more. So I'm going to write it out. So the full SVD includes the eigenvectors corresponding to any zero eigenvalues. Of A transpose A or AA transpose. Now, that being said, so then the eigenvector corresponding to the zero eigenvalues of A transpose A, those would be used to create the matrix V. So to get matrix V, you would have the vectors V1 through VR from like the reduced SVD. But then you would throw in the eigenvectors corresponding to an eigenvalue of 0 of A transpose A. And then those would form the remaining columns of the V that you need in the full SVD. Okay. And then similar for U as well in the full SVD. So it's basically the original U plus matrix in the reduced SVD. But then you're just going to add some more columns to it. And these columns would have been orthonormal eigenvectors corresponding to an eigenvalue of 0 for AA transpose. Now there's a little bit of a simplification of sorts that you can do here. So when you're looking for the eigenvectors corresponding to a 0 eigenvalue, let's see here. I guess let me use B to not confuse with A up here. But let's say you have a square matrix B, and you're looking for 0 or eigenvectors corresponding to an eigenvalue 0. Okay. Well, if the eigenvalue is 0, then you'd really just be looking for vectors in the null space of B. Okay. So that means that when I'm talking about getting the vectors like VR plus 1 through Vn, and I'm saying these are like a orthonormal eigenvectors of A transpose A, corresponding to an eigenvalue of 0. Okay. So if it's corresponding to an eigenvalue of 0, then essentially they're just going to be vectors that were in the null space of A transpose A. So you really just need to find an orthonormal basis for the null space of A transpose A. But it is a fact that for any matrix A, the null space of A transpose A is actually the same as the null space of A. So in fact, to get these vectors VR plus 1 through Vn, in fact, you just need to find an orthonormal basis for the null space of A. Okay? And that might be a little bit easier to just look at the original A and find its null space than to look at the null space of A transpose A, perhaps. Okay. Now, similarly, these additional columns of U, so they're supposed to be orthonormal eigenvectors of A transpose with a corresponding eigenvalue of 0. But to get these guys, you would just need to find an orthonormal basis of the null space of A transpose. And it turns out that the null space of A transpose would be the same as the null space of A transpose. Okay. So then really you just need to find an orthonormal basis for the null space of A transpose in order to get these vectors UR plus 1 through UM. Okay. And then for the matrix sigma, so it's going to have the singular values along its diagonal. But then that only gives you like a size R by R matrix. So then what you do is you just add zeros as needed until it's the same size as A. And that's how you get the matrix sigma for the full SVD. Okay. All right, so then I guess I'll try to do one example of finding the full SVD of a matrix, and then I think I'll end my review with that. And then we'll have Q&A starting at 3, okay? So I'll try to do the example up here. Okay, let's choose this matrix. Okay. All right, so for this matrix, let's try to find full SVD. All right, now this time my matrix A is 2 by 3. So the M is smaller than the N this time. So because M is smaller than N, I think I might go with method 2 to calculate the reduced SVD first, since A transpose will be smaller than A transpose A, okay? All right, so I'm going to start by calculating AA transpose. So it'll be 1 plus 1 plus 1, 3. It'll be negative 1 plus 1 minus 1. Okay, so it looks like that will be AA transpose. Now I want to find the eigenvalues and eigenvectors. So first for the eigenvalues, I'll do lambda I minus A transpose. So I'll get lambda minus 3 on the diagonals. 1 and 1 off the diagonal. And then here the determinant will be lambda minus 3 squared minus 1. So what I'll do here is I'll set it equal to 0. I'll move the 1 over. Square rooting gives me lambda minus 3, could be plus or minus 1. Leaving me with lambda could be 3 plus 1, so it could be 4. Could also be negative 1 plus 3, so it could also be 2, okay? So these were the eigenvalues of AA transpose. So then if I square root each of these eigenvalues to get the singular values, so here the singular values are 2 and square root of 2. So then for my matrix sigma that I need for the full SVD, what I'm going to do is I'm going to first take the singular values that we found and put them into a matrix as the diagonals or diagonal entries. And then I need this matrix to be size 2 by 3 so that it'll be the same size as A. So I'm just going to add a column of zeros to make it 2 by 3, okay? So in general, to get the sigma for the full SVD, after writing the singular values in the diagonal, you'll just add zeros as needed until you get sigma to be the same size as A, okay? All right, so next I'd find the eigenvectors corresponding to these eigenvalues. So let's try to do that real quick. So when lambda is 4, I'm going to get 1, 1, 1, 1 for this matrix. So then looking at the null space of this matrix to get the eigenvectors, we'll get x plus y is 0. So you could say like y is t and x is negative t, which will give us an eigenvector of negative 1 and 1 right now. So I'm going to go ahead and normalize it to divide by its length. And this time, the vector that we have here is going to be vector u1, okay? So since I'm looking at the eigenvectors of AA transpose, we're getting the vectors u, we're getting all the u's, I guess, rather than all the v's, okay? All right, so then let's take the next eigenvalue. We want to find a corresponding eigenvector. So to do that, we look at the null space of this matrix. So I guess that's x equals y. So then we take the vector 1, 1 as one particular eigenvector, and then we'll normalize it to get the vector u2, okay? All right. Now let's see, matrix A was 2 by 3. Since A was 2 by 3, the matrix U that we'd be looking for would be 2 by 2. So then with the vectors u1 and u2 that we just found, we actually already have the matrix U that we need for the full SVD, because it's already 2 by 2. Okay, so next, I'm going to calculate V1 and V2 as in the reduced SVD by using these formulas. Okay. Okay, so let's see here. For V1, that's going to be, so sigma 1 was square root of 4, so it would have been 2. And then A transpose was, okay, so this was A transpose up here. And then U1 was 1 over root 2 times negative 1, 1. So then I'm going to go ahead and compute all of this. That's going to be 1 plus 1 is 2. Negative 1 plus 1 is 0. 1 plus 1 is 2. And I guess I can cancel the 2's. So I'll get 1 over root 2, 1, 0, 1. Okay. And then for V2, that'll be 1 over, so the second singular value would have been the square root of the second eigenvalue, so square root of 2. And then A transpose once again, times U2, which was 1 over root 2, 1, 1 this time. So that's going to be 1/2 here. And then this would be negative 1 plus 1 is 0. 1 plus 1 is 2. And then negative 1 plus 1 is 0. So that's going to be 0, 1, 0. Okay? So then with these two vectors, V1 and V2, that will give me 2 columns for the matrix V right now. But for the full SVD, I need one more column to get my matrix V. So to get the third vector V3, okay, so let's see how that worked again real quick. So I'm going to scroll down a little bit first. All right, so if I need to find some more vectors for V, what I can do is I can find an orthonormal basis for the null space of A. So that's what I'm going to do, all right? So I'm going to find the null space of A and then find an orthonormal basis for it. Now, if I needed more vectors for the matrix U, I would have found them by getting an orthonormal basis for the null space of A transpose. But since I'm finding more V's, I need an orthonormal basis for the null space of A. Okay, so let's see here. A was -1, 1, -1, 1, 1, 1. So now I'm going to start reducing this matrix a little to find its null space. So let's say if I add row 1 to row 2, okay, and I'll go ahead and stop here and I'll write out the corresponding system of equations for the null space. So let's see here. So y is 0. And then with y being equal to 0, that means x will be equal to -z. So in this case, the null space of A was one-dimensional. So that gets me an eigenvector. Well, okay. So that gets me a basis for the null space of A. So since it's just one vector, I don't need to worry about making it orthogonal to other vectors, but I do need to normalize it to make it orthonormal. So if I divide this vector by its length, that will give me the third vector v3 that I need. Okay. So then that gets me the matrix V, and then with these three matrices here, we'd have the full SVD of A as U, sigma, and then V transpose. Okay. Okay, so yeah, so do you guys have any questions about that right now? Okay. Let's see here. Let's go ahead and take a break until 3 o'clock. So then I'll be back for some Q&A from 3 to 5. So if you guys had any questions, you can stick around and ask me your questions at that time. And if you guys have more questions about the SVD, I can try to address them. I had a lot more examples prepared, to be quite honest, but of course I didn't have time to get to them though. Okay. So let's come back at 3 o'clock.